The objective of this video is to explain exercise number 2 on your notes, which is an exercise in which you have to design a can shaped like a right circular cylinder and that contains 1 liter of any material. So the problem is asking you what are the dimensions that will use the least quantity of material. So what we have is a can like this shape in which the total volume will be given by the function the volume equals to pi times radius squared, which is the base of the base of the circle, times height, which is the altitude. But the exercise is not asking you to maximize the volume. It's asking you to minimize the material used in doing the can. So to minimize the material, what you have to do is obtain the area of that cylinder. And the area, it is a rectangle if you open the cylinder, plus twice the base, which is a circle. So the area of the cylinder will be given by the formula area equals twice the pi times radius squared, which are the two areas of the base and the top of the cylinder, plus twice p times radius times height, which is the area of the rectangle. So that is a function that we have to minimize. The problem here is that we have two variables. As you can see, we have one variable, which is the radius, and another variable, which is the height. So as we cannot obtain the derivative with respect of two variables, we have to substitute one out of these two variables. And to do so, we're going to use the other formula, the formula of the volume, because they are asking you to shape, they are giving you restrictions of this volume. They are asking you to shape to design a layer that contains 1 liter. So another thing to take in count is what is the volume with respect of the cubic centimeters. 1 liter, it's equals to 1,000 cubic centimeters. So in the formula of the volume, what we have to do is substitute the volume by 1,000 cubic centimeters, because that is the volume that is asking us to have. So the total volume will be 1,000 centimeters, and we're going to solve for h. So h is going to be 1,000 over pi times radius squared. And once we have h, we can substitute h on the formula of the area in order to have an equation or a function which is a function in only one variable. So now we know that the height or the altitude of the cylinder, it will be 1,000 cubic centimeters over pi times radius squared. Using this h, I'm going to substitute this h in the function of the area. So I will have the area, it is equals to 2 pi radius squared plus 2 pi radius times height, that in this case will be 1,000 over pi radius squared. So using this, we have now a function with respect of only one variable, which is the radius. And that function will be 2 pi radius squared, radius squared, plus 2,000 over radius. And that is actually the function that I want to minimize in order to have the least material used. So once we have our function, the function that we're looking for to minimize, we have to obtain the derivative of the function. So a prime of r, it is going to be equals to 4 pi radius minus 2,000 radius to the negative 2. Because remember that this term, 2000 over radius, can be seen as 2000 radius to the negative 1 in order to be able to differentiate it. And that's it. Now we have our derivative, which is 4 pi r minus 2000 over radius squared, equating this derivative to 0. We have to solve for radius. So first thing I'm going to do is multiply both sides of the equation times radius squared in order to be able to simplify this radius squared. So we'll have 4 pi radius cubed minus 2000 equals to 0. And solving for radius, that will be equals to 2000. So radius will be equals to the cubic root of 2000 over 4 pi. If we divide for 2000 over 4, it is the cubic root of 500 over pi, that if you use calculator, and that will be 5.42. And what is this? This is centimeters. We were talking about cubic centimeters, but when we obtain the cubic root, that is 5.42 centimeters. What does this mean? That means that the radius that will minimize the material used in order to build a cylinder, it is going to be 5.42 centimeters.